So most interesting part is hidden from you yet.
Yeah, pretty much. But I think we're getting towards that step.
Okay. Yeah, I was for the first time in Dr. Rogers' lab yesterday.
Yeah.
I was guiding a tour and just bringing visitors to different labs and listening to the stories.
Kent was telling stories
Yes. So,
about what we do.
well, it was only 5 minutes for all his stories.
Oh.
Just briefly summarize the activity.
Yeah.
Showing the instruments and trying in a humoristic way explain what they do or what if they do not do what they have to do, why it happens.
Yeah.
And you don't graduate this year, you have 1 more year to go.
Yeah.
Enough time to enjoy this on instruments.
Yeah. Yeah, we're still getting some of it set up. That's sort of what we're still trying to get a lot of the lasers and stuff set up from when we moved over. So that's what Ken's been working on mostly this year so far. Is because he had to like pull everything apart and I was trying to put it all back together.
I see. So I know that there was Zach, but he defended.
Yeah.
There was Olivia
Yeah.
active. There is you. Who else are?
It's just Olivia and I right now.
You guys need more stuff.
Yeah.
It's a huge lab with very ambitious research. So
Yeah. I know. And Olivia's getting towards the end of her time too. So then.
In sense of defense, not Jane.
Yeah. No, she's not dying. Yeah. So then I don't know. We had a couple other undergrads. Like in the summer and last year, but none of them stayed this year. So they need more undergrads and grad students. So
Is there a discussion of you applying to grad school here and continuing in the same group, or
we haven't talked about it. I don't know if I haven't really figured out if I want to stay or not.
you are for grad school, or you don't care, or you?
Yeah, I'll go. I just don't know where.
Yeah, we have 4 waves of high schoolers who consider NDSU for their undergraduate studies. I've checked in private what are our competitors, and like they are going either in NDSU or Madison, Wisconsin, which I think hard to compete with.
Yeah.
The hope is maybe medicine has substantially higher tuition and it will drive students towards us.
Yeah. It's a good school though, but yeah, it's very expensive.
Yeah.
And there's a lot of people.
I visited this July for a conference, and it's very inspiring arrangement on the campus.
Yeah.
Like, we don't have a lake on the campus, so even with all other things being equal, it's one of them.
That'd be nice. Yeah.
And they have they go dipping into the lake like for swimming. They take a sailboat.
Oh yeah.
And they have like cafeterias with a lake view, so it's something we are missing here.
Yeah, we don't have very many good views here.
First floor, new building is okay.
Then you can see campus at least.
Yeah, you need to convince yourself that there is nothing more beautiful in the world than our campus.
Yeah, that's true.
How's it going?
Right.
Excellent,
How's
thank
the
you.
ankle holding up? Oh, you got your special stock on.
Yeah, I got my sleeve.
You get like a brace.
Yeah.
What are you wearing shorts for?
It's gonna be
It's
like
still
six-
like-
It's gonna be like 70
cool.
degrees today.
Really? It was like 40 this morning.
I didn't leave until an hour ago.
It's,
You had to miss your tour and everything?
Yes, bro, I woke up in the middle of, I sprained my ankle yesterday. And I woke up in the middle of the night and I like could not walk right.
Believe you. How'd you get here?
It's like a bit better now because I used to
Hop on one
like an
foot.
hour. And I just kind of like hobble.
Just take like a handful of ibuprofen every couple hours.
yeah.
You'll be right. I do not recommend taking it by the handful though.
Okay. Just by the recommended dose.
I don't know what the recommended dose is. I usually do like 3 or 4.
It's like you can't surpass a
3 or 4
certain
of the
amount in a
200s.
certain number of hours.
Yeah.
And I don't know how many that is.
I have a rough idea, but I couldn't tell you exactly how much.
I
No.
take like 2 out of 10.
Oh, I'm sure you can Google it, yeah. No, it's that kind of
That's
stuff is
kinda like-
restricted.
That's gonna destroy your liver. Right?
I actually, don't take ibuprofen very often.
You take other shots.
No, not anymore. No. God, why would you think that?
Well, this is our class.
but without Melody, we will all
I
go.
know.
Makes you feel any better? This is exactly how many people were in the class I just came from, so,
Really?
yeah. In order.
Is that normal?
Normal for a Friday, yeah. Usually we have like, maybe 5 people show up on a Monday and a Wednesday. And then on Friday, it's usually like maybe 3 of us. Typically, that's pretty common.
So which class?
Inorganic. With parents.
Okay, oh, I was passing by this in the first
In
floor.
124, yeah,
Okay.
or in 118, not 124, that's the last.
So what do you study now?
We just started acid base stuff. Going over like, the different. Like definitions of it, I guess, like depending on what kind of, if you have like protons or not in your molecule.
Mhm.
And how well like like hard and soft acids and bases.
Mhm.
And how well like they react together, like you want to react like a hard acid with a hard base.
I
And
see,
such,
I see.
yeah.
The coolest thing, well, I never had any chemical background except high school, but to what I've heard, the most attractive and cool part of the inorganic chemistry is ligand field theory.
What?
Ligand field theory.
We are working, I guess we have been working with like ligands, at least in lab, like all semester. Now we're kind of starting to talk about it more,
But
like ligands and like coordination complexes. and stuff, yeah.
Right, but I'm sure you guys have it maybe based from the freshman chemistry or from common knowledge. How many d orbitals transition metals have? D orbitals, yes. What is if the atom is just floating in the free space? What are the energies of d orbitals?
I don't know, I should.
Do they have the same energy or different?
For the orbitals that degenerate,
The orbitals are degenerate, right?
Yeah.
In a free space. But as soon as transition metal is, it may be oxidized to some oxidation state, maybe not, and then it coordinates with ligands. What happens to energies of the orbital?
they stop being degenerate. They change. The orbitals, the energy in the orbitals changes.
Okay, orbitals stay the same, but they
The energy, sorry,
But-
energy.
Depends what it's coordinating with, I guess.
okay. And
We go up or down.
which typical coordinations do you remember? Come on, you all guys know.
Well, I mean, if it's coordinating with something that has like a HOMO that is in like a lower,
No, just geometrically,
Oh.
what are typical patterns of coordinations? How many neighbors, how many?
how many can it have?
Yes,
It depends on it's not the oxidation number you have.
I'm pretty sure you can have up to 8, but that's like
okay, but what is most typical? What is most typical?
4 or 5.
4 is okay, 5 is a little exotic, what else?
Well, you could have
6.
6 too, yeah.
Okay,
Okay.
and how do 6 ligands coordinate? What are the angles between, if one makes a ligand,
30, right? Or well,
metal ligand, what would be the angle?
I don't know. I know I would be able to draw it for you.
90.
Okay,
And what is
I guess
the,
that makes sense.
what is the typical name for this coordination?
That is
Starts with letter.
octahedral.
Yes.
Yeah.
So you guys know of the ligand field theory, and the d orbitals, how do they split? It's only partial lifting of degenerate. So one group of orbitals go down in energy, another group of orbitals go up in energy. So in lower energy, there are how many?
3.
3,
And on the top.
just 2 then.
No,
So now you can pass, like, well, maybe not the whole exam on organic, but at least with guarantee you can get through basics.
All right, yeah, I mean, we haven't gone over some of that stuff.
But
others,
which for it, it's something
yeah,
very universal, very useful. If one gets tetrahedral with 4 neighbors
yeah,
in a pyramidal shape, then it's swapped differently. There are 3 on the top and 2 on the bottom. And all others, tetrahedral and octahedral, are easy.
we have gone over, we actually have done this, I have it in my notes, I just remembered. Yeah, but we talked about it in like a different context where we're like building like MO diagrams from it.
Yeah.
So that is like an octahedral splitting. And then the tetrahedral splitting would be the other way around, where you have 3 on top and 2 on the bottom, and you have that. Like the switch, this is like the difference in energy, I guess, from the very center of the one that it starts off with. And
Yeah,
so
and it literally says.
yeah. I know that we've done it. I just forgot. I think we literally did this like 2 days ago.
Okay. I didn't know what I was curious. And everything more complicated than octahedral and tetrahedral is not possible to memorize for simple guys, but professionals do. Everyone may need to know what is a ligand field splitting for square planet. Did you hear about it? Not yet.
I'm gonna have to.
Yes, because I bet you work with porphyrins,
Yeah.
like enzymes, filled with like little porphyrin molecules, with whatever iron,
Yeah.
right?
Yeah.
And then these porphyrin molecules do have 4 nitrogens arranged in one form. They use partially charged negative nitrogens, approach this positively charged iron, and they split energies. And splitting of the energies of iron is responsible for their enzymatic activity.
There you go.
I need to probably stand up and walk around and say something smart. I'm just a little less energetic. But
Take a group trip, get some coffee. I could get some crutches for Ava.
I'm thinking maybe we should have a coffee party each Wednesday during the lab.
Yeah, I will totally bring some coffee. I've been looking for people to make coffee for. None of my roommates drink coffee. I have so much. I love making coffee. Yeah. All right. You got it. Yes.
I do know my number in coffee. You know?
Yes.
What do you got?
Can you make some other,
Yeah, I could, I don't know.
make non-American,
Make like a.
make whatever coffee.
You like, have you had hot chocolate?
Yeah.
Okay, yeah, so I'll make
There you
you
go.
some, like a good mocha with like just a little coffee and hot chocolate and milk.
Perfect.
Yeah. I'll-
So imagine Melody telling back to the subject. I do not want, but I have to. So we do have two lectures squeezed into one because I sacrificed one for Slater determinant. And I'm just less energetic because I fear to get over less and less time and more material per unit of time. So all the previous things that we were doing, yeah, I can probably shouldn't see.
There we go.
I see it in your group. So everything we did before, we have our class used 1,000 theories and two applications.
Yeah.
Now we will get to the 2,000 series and maybe 3 applications. Before we were applying all this quantum things towards electrons. But as chemists, you can define that molecule is a collection of positively charged nuclei and negatively charged electrons. Electrons move so quickly that they're so mobile, they form these orbitals, but some nuclei, especially protons, are all a little slower, but they're 1,000 times or 2,000 times lighter than electrons, but still moving relatively quick. And instead of thinking of ions as point charges, like nailed down to certain position in space, they are allowed to move, and they are allowed to move in a quantum sense. They can be like bond can be a little longer, a little shorter, and we have probability distribution for distance interatomic. And one can quantize the motion of nuclei.
Oh.
Nuclei. So if we practice the same Schrodinger equation, we just need to update them. One constant will stay the same. Mass will be a little bigger because ions are heavier than electrons, and charge is the same as for an electron, right? And the potential for electrons, we do not know what we know from common background that electrons are attracted to ions in like this Coulomb potential, but we didn't study it yet. In free space and in the box, it was just some square potential. We do need to design a potential for interatomic bond. What happens if we elongate the bond? What will be the force? Force direction.
Okay.
The force direction of what? Of the bond or the
If
what's pulling it apart?
if I
Be
pull
away.
like HCl, I take H and try to pull it away and release. What would it do?
Go back.
Right back.
So the force directed
Where's the electron?
opposite direction of elongation.
Yeah.
Okay.
It's like a returning force.
Yeah.
If I take this proton, hydrogen, and try to push it inside, and then release, what would it do?
It also goes against
Opposite of-
where your force is.
Okay, so it's like returning force. Wherever your elongation and contraction force is against it.
Yeah.
Right? What if I do not do anything? What is the force?
Well,
No force.
Yeah.
So if I contract it stronger, the force will be stronger. If I elongate it stronger, it will elongate stronger, right? So how the force depends on the value of elongation. We don't need any math, we can do philosophical. It's
Oh,
zero
like that.
in the equilibrium, it is opposite, and it is increases as we go away.
Inversely
Inversely proportional, okay, one option, another
or
Negative,
bet you
negatively,
direct, negative, direct, negative,
I bet you-
inversely.
okay,
it's like
Yeah,
an
yeah.
It's
exponential,
negative.
like increase though.
He said the longer the elongation, the higher the force, right?
yeah, so it can be linearly with minus sign, right? So,
Is it?
yeah, who was scientific competitor of Isaac Newton?
Oh, man, I don't
Trivia
know my
question.
history.
True question.
It's not Plato.
In the English, his last name is equivalent.
Galileo.
to- Yeah, so Hooke's law, what does it tell? The same,
Oh, man,
you basically,
Basically, what you just explained.
or you just explained. Force is,
Yeah.
returning force is like minus kx,
Oh, yeah, okay, yeah.
okay? So if force is minus kx, what will be the potential? How do we get potential out of the force? We discussed that gradient derivative of the potential gives force, and what is the operation opposite to derivative?
Changing force and changing
Integration.
the reverse of the.
Integration, right? Derivative of potential is force, integral of force is potential. What is the integral of minus kx? We don't need paper for this. What is integral of x?
X squared.
Yes, and if it is minus k in the front,
Minus K X.
and when we have integrals of like x to the power n, is it just ramping up power innocently, or we need to pay for it? Is there any factor?
There's a
Divided by
factor, yeah,
Good. Is this factor connected to the power?
yes,
How?
it is one over the power,
Perfect. So x, integral of x will be,
1/2 x squared.
and if we have
Oh,
k,
one
so kx squared over 2. Do you remember it from high school?
Yeah,
So kinetic energy of the spring of the.
yeah, that's what I was thinking, is that it's an exponential, but I was thinking of it the wrong way.
Oh, but about exponential,
So that
you're not.
the force does not increase exponentially with length. But the energy, like the potential energy of it increases exponentially with the force.
The small elongations are described very well by Hooke's law and quadratic potential. If one really wants to break the bond, then the potential is more difficult and it has like exponential component. It's like more general, Morse potential, and we can go over it. I think I do have it in this way. Okay, but in the simplest way, it is like harmonic potential. So our potential energy will be something x squared, and kinetic energy will be the same as before. So this is Schrodinger equation for one bond distance. We can expect that if it is a returning force, mass on a spring will do what?
Pull back the other way.
And there is a colloquial smart thing. If something goes forwards and backwards with this regularly,
It is
harmonic, or if there is a
vibration.
harmonic vibration,
Not the word.
well, those are good words. Did you saw
It's like a stretching vibration.
wall mounted cuckoo watch?
Yeah,
Yes.
yeah,
What does it have on the bottom?
or wave pendulum.
Yes. What does pendulum do?
Oh, it swings.
Swings. Okay. Harmonic swinger. So the chapter is harmonic swinger.
Okay.
I'm not sure if my colleagues will approve it. Okay, what else? Like swinging, vibrating, just let's play. words.
Oscillating?
Yes.
No.
So the chapter for next, whatever, 3 weeks will be harmonic
Oscillation,
or harmonic oscillator,
okay,
quantized harmonic oscillator.
okay.
So we do have Schrödinger equation for quantized harmonic oscillator, right? We just keep the same kinetic energy, we put quadratic functions there, and then we do need to solve it. Later on, we will be curious to find some time-dependent problems, right? Because it's so cool. But at the beginning, we need to find eigenstates. Right? And so, so the challenge is to find in narrow sense equations exist with a purpose then to be solved. So if you do have Schrödinger equation for certain systems, we need to find eigenstates, eigenvectors, and eigenenergies. And this is a challenging problem that is not solved as easy as we did for particle in the box or for free space. It's one of the first serious problems. Basically, starting from today, in some sense, we just starting the course. Before it was a little wake up exercise. The true science starts on the now.
Else for weeks is just a warm up,
Yes.
okay.
So I probably need to cover two things. One, who and why needs this quantized harmonic oscillator, and second, what is our strategy and philosophy to find its eigenstates. Who needs to the nuclear vibrations, chemical bonds to be elongated and have them their properties at the quantum level? Why do we do it? Then we did you do FTIR?
Actually, we did talk about it a little in analytical and also in inorganic,
Okay,
just a little bit.
okay.
Yeah.
So do we need any quantization for FTIR, or you can go classically? Or like teach, please teach.
Oh, no, I
teach
can't teach you about it. All I know about it,
What does that stand?
Fourier transform. So all you're doing is just switching the, you are changing it from like a time domain to, God, I forgot whether it's to like, yeah, the frequency, and then a computer program like smooths out all the noise and stuff, and then you switch it back to time for frequency. And you have like a cleaned up
Okay.
spectra, basically.
So you get normal modes frequencies.
Yeah.
And they are very specific to each atomic group.
Yeah,
So
and that's where like at those frequencies, man, I wish I remembered all of it, but
you do really well.
oh no, I don't think I am.
Yes, it's
I think
humble.
it's somewhere in one of the.
You can just read this book.
I forget what the significance of like the frequencies, like with the peaks actually are. I know for a fact that I just talked about it like a week ago in class, but
It's okay.
Okay,
yeah,
so
we haven't done anything with it, so I forgot.
the benefit and goal of any spectroscopy, including FTIR. Now I'll just check if anyone. I know they are in the car traveling, but just in case if anyone wants to join us by Zoom, no.
I don't know.
I doubt that. So the goal of any spectroscopy is to, by signatures, by spectroscopic signatures, identify structure of molecules. So it's like a photograph, right? And the frequencies of normal modes for lighter atoms, frequencies are higher. For heavier elements, frequencies are lower. Like if the molecule has CH bond, it will be at about 3,000 inverse centimeters, about 0.4, very high. If there are no high frequencies, if there are like only if we design a molecule with only like nitrogens, carbons, oxygens, or proportion of hydrogens is very low, frequencies will be in like 2-3 times smaller. And just by looking on the FTIR spectrum, one can say what is composed of, or what are the bonds.
She could have told you that. Talked about it in OChem
Yeah,
last year.
well, I only
Yeah.
remembered it just now when you said it.
Okay,
Yeah,
so like double and triple and single bond would have noticeably different frequencies. I'm not going to say what the molecule is.
yeah, we did like actually a ton of that.
Oh, okay.
Last
Like
year,
too
like
much.
figuring, like, yeah, we had a spectrum, and we had to. You just figure out the structure just
Yeah.
from the spectrum,
Based off
yeah,
of the features of the peaks and how broad they are. and
Yeah.
How
That's
many
cool.
there are and things like that.
I learn a lot. You are well prepared. So if you basically do not need this course, my only goal is to make connections. Like you have all materials, all building blocks, and I just glue them together.
all right.
Do my best. Okay, but if we try to squeeze our brains and remember the best we can about high school vibrations, like Hooke's law is F equals minus kx. Then there is a mass, and there is a k is elasticity constant. And how does one get a frequency of oscillation based on elasticity and mass? There's an equation.
Probably.
That's
That's what I know.
you do know it. You do know. You just need to scratch deeper in your memory.
Yeah. Take deep breaths.
So, how does frequency depends on elasticity? The stronger elasticity, the smaller or lower the frequency, like
You would need a lower frequency for,
lower.
for stronger force, like if the. E,
Strong force returns spin quicker.
yes, so
Yeah.
you,
Quicker
Higher
means
frequency.
yes, right?
I'm trying to,
Vibrate faster.
Vibrate faster, yes. Stronger elasticity, vibrate faster. Very good.
yeah,
I agree.
okay,
Now, for mass, which is a measure of inertia, higher mass for the same spring, you oscillate quicker or slower? Because the same
lower.
yes. So we have elasticity and mass. Elasticity increases frequency, mass lowers it down. So just philosophically and hypothetically, it should be elasticity K divided by mass. And maybe if we do, I need to work on pronunciation. Elasticity divided by mass.
Oh, I think you said it right the
Yeah,
first
that's
time,
good.
yeah,
And if you do math,
Oh, math versus mass.
yes, everything carefully, then it should be not just fraction, but square root of
Okay.
elasticity over mass. Okay, so it is a frequency.
okay,
So this is enough for each group of molecules. We can find elasticity, we know mass, and we can get frequency, and we can identify groups of molecules. So for FTIR and your organic analytical, we do not need quantized vibrations. So it is like useless chapter. Looks like, right? So let's think further. In which other experiment we need quantized vibrations? Who is Raman?
We talked about Roman
Did we
briefly.
in this class or
Yeah,
any
in
more
this class.
class? I don't remember what did you talk about.
I don't know either. I just know you were asking about ramen, or maybe you were just like what it does,
Okay, what did
and then I didn't know.
Oh, okay.
But I felt like I should, because we do that, but I haven't done that yet.
Does your lab have Raman?
Yeah.
Okay, then you should know it.
Oh.
So anyone else has a Raman spectrometer in the backyard?
Does Seth have one in his backyard?
Not that I'm aware of.
Okay.
I'm just a lowly.
Urban.
Yeah.
Check in your lab. Maybe it does.
I'll ask.
Yeah. Or maybe there is a shared facility, and for some of your conjugated polymers, you may need it. So yeah, I'm wasting time from equations, but maybe this informal.
This is more enjoyable.
Well, from myself.
I know that we talked about Raman spec
Yeah.
in both analytical classes, but I couldn't tell you anything about it.
But any keywords.
Yeah, no, like I have no recollection.
Do you know what it looks like at all?
No, because we never we just talked, we literally just so analytical with Gudong was like just going over like 20 different methods in one class, like as quickly as possible, and then just moving on from there.
Okay, I'm trying to compete with these 1,000 methods and 3 applications. So suppose we do have 2 quantum levels, like HOMO and LUMO of a mole, electronic levels. And we do have visible spectroscopy. We just promote the electron from HOMO to LUMO, or we stimulate it to relax back from LUMO to HOMO. How does frequency of the light refer to energy difference of these levels?
Bet you the frequency is proportional to the jump.
Or even equal?
So higher, the bigger the jump, the higher the frequency.
Yes, it's equal. Yeah, the bigger the jump, the higher the frequency. The lower the jump, the lower the frequency. And if we dare to use frequency of resonance, which will be bigger than this energy offset or lower, the interaction between light and matter will not happen. So the molecule will be looking as a transparent glass for this frequency of light. So in order for light to be captured by a molecule, its frequency, monochromatic light, should be in resonance, should be exactly like frequency of light times Planck constant should be exactly equal to energy difference. Or energy difference divided by Planck constant should be equal to the frequency. You don't object. No, it's kind of common sense. Now, is it possible to design such an experiment where we know for sure that the molecule has only 2 levels, all others are far away? They do not contribute. Only 2 levels. We know their frequency. And the spectroscopic signals appear at lower frequencies or higher frequencies. That sounds crazy.
Is it? What do you what's what are we exactly trying to
Okay,
find?
so
Where they are?
Suppose I have a molecule where I can neglect all levels except HOMO and LUMO, and their energy offset is, let's say, 2 electron volts, which will be like yellowish, greenish. I create a monochromatic laser light of different frequencies, and I find that it absorbs, the molecule absorbs and emits not only at 2 electron volts, but like 2.1, 2.2, or 1.9, 1.8. Would it be crazy?
I don't know. Doesn't sound like it'd be too crazy.
But if you're, it's not more craziest than all these things.
No.
Yeah.
But if you take a common sense that we have only 2 levels, only 1 photon, and suddenly it play a role by a substantial mismatch, it's a little unusual. And the reason for this is that in addition to pure electronic levels, there are because of nuclear motions,
It's going like back and forth.
Instead of going by back and forth, they form a quantum potential with quantum levels, and these additional quantum levels contribute to resonance frequencies for spectroscopy. Okay.
Okay.
And if it is just absorption and emission, it's just molecular spectroscopy. It's normal. You need this quantized nuclear motion for this as well. But Raman is one excites at one of resonance frequency, emits at another of resonance frequency, and then looks for their difference. And by this Raman spectroscopy, one finds energy of sets of this individual quantized level of nuclear vibrations. So if we read through what is Raman, if we practice this spectroscopy, it will be like glowing evidence that nuclear motions are quantized. Why, for which features one uses Raman, I will be really happy to learn from you guys one day, or maybe it will be too late after this course next year. If you didn't graduate yet, you can be a special guest to the same lecture. You come and tell,
Wow.
hey kids, Raman is needed. So just think about it.
Fred, you can come back.
Maybe, yeah, a little,
Trip down memory lane.
yeah. Oh,
Okay, so enough for motivation. You more or less convinced that nuclear motion can be quantized and we can get benefits out of it.
Yeah.
That some practical labs use it. Why? I just skip it because it's very far from my specialty. But for sure, Raman got Nobel Prize that someone needed it.
Yeah.
Okay, now practically, I will show total amount of slides is like, I don't know, 60 or 80, and half of them.
Yeah, 70 in between. Okay,
thank you. We'll go through them. So one part of the slides will be on what we already discussed, Schrödinger equation and necessity to solve it, and just discussing the shape of the potential energy circuit for potential for vibrations. And another will be in new philosophy, how to solve the Schrödinger equation. Yeah, there is still time to quickly smash through. So there is a big mathematical challenge with quantum theory, and it is why not everyone loves it. So even some people who consider themselves more or less successful in math, in calculus, and even in differential equations, still may hate quantum theory. And even with the classic someone started talking about.
I'll be back.
So did you put differential equations or only?
I haven't taken it.
Yes,
I did a semester of it.
in the past.
Yes.
Okay, so when we were practicing some very simple differential equations here in the past, our answers like were looking like exponential sines and cosines, right? Would you agree with all?
Yes.
So exponential sines, cosine, polynomial functions, they are elementary functions. And it is really cool if solutions of equations can be expressed in terms of elementary functions. But the major challenge of eigenvalue problems, of the problems that pop up in the quantum theory, is that some of them do not have solutions in terms of elementary functions. So there are so-called special functions which are intentionally designed as a solution of a given problem, or the special functions can be expressed as infinite series summation of elementary functions. So the solutions of quantum problems have such crazy shaped functions that elementary things are not insufficient to describe them. And it is the reason why, well, we are trying to simplify quantum theory as much as possible, but we need to recognize this challenge, even if we try to avoid it everywhere as possible. And solutions of such equations are also not easy. So if you open basically any textbook on quantum theory, look for a chapter of harmonic oscillator, they will immediately give the answer for eigenstates, which will be in special functions, or give a way how to get them through summation of a series. This is correct, this is cool, but it is too much for our quick introductory course. So I do have a plan, a lot of philosophy that we will avoid the excessive mathematical challenge, but because there is a law of conservation, I cannot get everything for nothing. Right? So we will replace mathematical effort, we will lower mathematical effort and increase like philosophical, general intellectual effort of just thinking about things. Would you, Patricia and Fred, would you please summarize to what we discussed here?
Sorry.
In a much
That was a
simpler,
lot.
in a much simpler way, and I cannot expect that anyone is watching recordings, but therefore please try.
So, with these differential equations,
Okay.
it's really nice if you're able to describe something in terms of like a sum of some simple, like just some basic functions, right? Right? But sometimes that's like super hard. You have to do like way too much complicated math. So we're not going to do that.
Oh, but it'd be nice. if
But we
could.
are going to think about the concepts more as a result of not having to do quite as much math.
Okay.
Okay, yeah, I'm happy. You did it much better than I. So, different ways, different brands of Schrodinger equations for different systems do have crazy solutions, and elementary functions are not always helpful. Like before, we had solutions for our equations like sines, cosines, exponentials, and sometimes there are functions for which there are no names. They are neither sine nor cosine, no polynomial, no exponential. There's so-called special functions, and it is a main reason why some people hate quantum theory. Standard way to represent special functions through infinite series of elementary functions, and all textbooks on quantized harmonic oscillator use the Hermitian functions for its solutions. Instead, and they are done by plugging in infinite series into Schrodinger equation and find coefficient of this infinite series, which is doable. I say just a little more crazy, but mathematically simpler and more elegant way. I'll probably tell everything and then go through slides, because if I try to mix them, probably fail both of tasks. Suppose I do have a basement, and I am a silly robot who follows your command. And on your little remote control, you have two buttons. Robot Dmitry, jump one ladder up. Robot Dmitry, jump one ladder down. Sure. And then you know that, for example, in my basement, I have 10 stairs. And you're angering me. You like, go one stair down, go one stair down, go one stair, and then there is no stairs more. No, go one stair down. What happens? What would happen to you?
Function.
Not functioning, falling down, something will go wrong,
Yeah.
right? So this is a philosophy of our mathematical theory. So we will assume that solution of this Schrodinger equation in harmonic, in parabolic potential, you have levels. We will suppose that there are remote vibrations go one down or one up. And then if we stay on the level number n, we tell go down, it will be n minus 1. And if you stay on the lowest level, number 0, we tell go down, and it goes sorry. It's mathematical paradox. And by this mathematical paradox, by trying to jump lower than basement, lower than floor, we will get a differential equation which is like not 100, but at least 20 times simpler to solve than original equations that are quoted in the text. And through this exercise, we are going to get the not all solutions, but only the lowest solution, the ground state of the harmonic oscillator. And the answer will be just Gaussian function in some shape, luckily for us. So this is basically it, right? I'm going to arrive to this step by going through 75 slides in 10 minutes. And what will be the challenges? So that your classmates will miss because of not attending here. So when we want to design this remote control that tells robot goes one level up, one level down, we don't have any operators except like inner potential, kinetic, position, and momentum. So these operators up and down need to be formulated as a linear superposition of known operators, like position and momentum, with certain coefficients. And the coefficients with which proportions position and momentum needs to be combined to manipulate quantum level is, for me, is a challenge. I never remember it. Therefore, maybe on Monday I'll do it. So I'll try introducing them down. And as soon as we have definition of this, the up and down operators, they often called considered in the ladder. They're called ladder operator, and some people call them creation because one create one more quantum, one more excited state, or annihilation when one annihilates a portion of energy. So our main task for today is apply annihilation operator to the ground state, and through this operator to get the functional ground state, which will be, I promise, very easy. But the linear coefficients, how to design this annihilation operator, is something to look on and try to memorize as a preparation for Monday with a quiz. Don't really know who work, but trying to squeeze our partners. Okay, so let's start our marathon over 75 hours. Today, for myself on the camera. It's not myself, it's only. Too much fun. We need to show something related to the press.
It's 75 slides.
Yeah, start.
It's because there's like blank slides in between, so it's actually fewer.
Oh, okay. So really easy. This is a set of problems that you need to present in those problems. Subjects in 2 weeks. We'll do midterm number 3. So one day we will just, and it's all based on the code number 2 that we started on Wednesday. Those are just some of the aspects. So in our space of theories, we jump to the system number 3 harmonic oscillator, and we start with Schrödinger equation. Here are example of vibrations that you know about more than I do. For your FTIR, here is just one nuclear mode. It oscillates, but at the same time there are quantized levels. There are examples of vibrations like librations if a solid molecule changes angle, if there is a magnetic and electric field in the radio generating LC contour, and many other things. So the interatomic potential, what Fred was trying to tell, it is more complicated than harmonic. It has repulsion and attractive part. But if you look on it near the equilibrium, one can approximately look on it as the elongation from equilibrium and put it as in a Taylor series. So the potential will have the equilibrium value. First derivative will be zero if it is a returning potential, if it doesn't have general slope, and then the first non-zero term will be quadratic. So meaning of the Hooke's slope constant is the second derivative of the generalized potential energy surface over the bond length, and it is what is our K coefficient. If we do a little math, we can assume that equilibrium has zero energy, and elongation is just one coordinate, and then our Hooke's law potential energy and the equations that we consider. The elasticity in the numerator, mass in the denominator give frequency, or angular frequency squared times mass will be K. This is a typical functional form used for potential because it literally includes frequency. So m omega squared over 2 elevation squared. So we do need to plug it into a Schrödinger equation, regular kinetic energy, potential energy, and find eigenfunctions and eigenstates. This equation has same kinetic energy as before, but here, in addition to independent function, it has function multiplied by r squared. This we don't think make equation almost insolvable. It is short writing, but dramatic increase of the challenge. Typical one solves just in a series, but we will do a trick that we did discuss. The answer that we are going to get for the ground state will be exponential as a power of r squared with some width, and the ground state will be one hump structure, same as for the particle in the box, right? So how do we get it? We assume that there is a set of eigenstates, and we can jump between them. And if you try to jump lower than the lowest state, this annihilation operator defined by phi naught will be zero, just philosophically. Then we need to design this phi naught operator and solve differential equation. There are several ways, and they're a little vague. So if going up and going down one after another keeps it at the same level, and energy level, number of level is proportional to the energy, then this creation and annihilation together gives us Hamiltonian, gives us energy. Make sense? And then on one hand. On another hand, Hamiltonian is momentum squared and distance squared. So these two representations of Hamiltonian must be equal. And by making them equal, we will find how to express a dagger and A in terms of position and momentum. So by putting some unknown coefficients in front of R and P, giving this A dagger A plus 1/2 should give us the original Hamiltonian. So basically one needs to solve for this unknown four coefficient. And if one does careful the maths, finding this all the coefficients, one can arrive to a solution. Or that A dagger is m omega divided by h bar and in front of r, and 1 over m omega in front of p. And momentum creation and annihilation differ only by the sign in front of imaginary unit. In previous years, I was giving like 2 lectures to derive these equations, but now we just skip because it is a technical video. But it's critically important either to derive or to memorize. So try to focus. It's really challenging to find these coefficients and find like how they differ from each other. So now if we admit that this is true, then annihilation operator acting on the phi naught can be formulated in this way, and momentum operator must be replaced by our definition of momentum operator, right? Derivative over space with imaginary unit and time. So, in this differential equation, we'll have linear distance, linear derivative multiplied by unknown function. That is something we can do. So, how to solve this equation? It looks like independent variable times function plus derivative of function over independent variable. We skip coefficients behind. So we can do separate variables. We can put everything related to the function to one side, everything related to the independent variable to another side. We leave them to the left and right, and then divide both left and right by phi, and multiply both right by dr, right? And then on one hand, we will have d phi divided by phi, which will be log of integration, and on another will be r dr, which will give r squared of the integration, right? I know that I'm kind of a couple of minutes. I need to return them to you back at some point. So here is what we get for solving, right? And then we do get on one hand log, on another hand r squared over 2. If we take these things into the power of exponential, e to the power log will be function itself, e to the power r squared will be Gaussian function. Therefore, ground state of the harmonic oscillator is Gaussian exponential, e to the power minus r squared. The careful solution of this problem brings us the value of the width parameter, right? Which is Q bar divided by m omega. And the normalization constant is another exercise that we need to postpone to the next meeting. So, again, function centered at equilibrium, it is Gaussian, similar to ground state of the box because there is only one wave. Okay, and somewhere, yeah, normalization should be postponed. I think we are done. Have a nice weekend. I can stay here and answer any questions, but I don't anticipate. Looking forward to see you on Monday. And there is a dedication of ice course, and about this time they offered ice cream. So if you come to the Sugihara, the third floor, you may get early sleep.
Going there anyway.
Little ice cream at it for lunch.